Eccoci qui, riprendiamo allora con la seconda parte e il secondo Innovation Talk dal titolo Unlocking Performance for HPC and AI, the symbiosis of compute and storage. Il primo relatore Paolo Bianchi, EMEA South HPC and AI Business Dev Dell Technologies.
Questo. Ok. Preferite che la faccio in italiano o in inglese? How many non-Italian speaking people are there? Please raise your hand. Okay, significant. So, okay, I will go in English, if that's okay for everyone. Okay. So, good afternoon, everyone, and thank you for being here. Let me first of all thank the friends in E4 for hosting us also this year on the stage and at this event. I was supposed to do this presentation in 15 minutes, but I only have 7, so I try to stay in the time slot. May I have this one? Okay, thank you. The idea for this very few minutes is to take a typical workload, which is common in AI, which is the creation, deployment of a model, and analyze what are the factors affecting the performance from the storage perspective more than from the compute perspective, which is the standard perspective any of us is used to see. No, so we put a lot of attention on computing power, interconnects, and whatever else, but we have also the storage. And that just to show that the results is the interaction and interdependency of a lot of factors. Now, in the typical 3 stages of a model creation, I believe the most challenging is of course, the training. So everyone is focusing on the training. Okay, so we have basically 3 stages: the data ingestion and data preparation, the training, so what we call model deployment, and the inference, model development and inference model deployment. Okay, so as you can see, all of them impact on the storage and on the compute. We will focus on the training, which is the most challenging of all 3. So what basically a system does when it does the training? The system loads some data, what we call the training data set from the storage, does the computation, and from time to time writes some checkpoints on the storage. Checkpoints are basically the snapshot of the status of the computation that are used to recover in case of failure, because training can be even very long. So if I have 1 week of training and I have a problem on the 6 days, I've lost 6 days. So the idea is to try to recover from where we are, or run some checks in the model. Okay, so we basically read and write from storage. Let me just put the point of one less considered aspect is the data loading. If we have a huge database, images, text, whatever else, we just don't read the image. We read and we prepare what we call data batch in a tensor form. And this is a process usually performed by CPUs and not GPUs. So this should say us that neglecting the role of CPUs in an artificial intelligence system can sometimes be a mistake, because we may slow down on the CPU side and on the GPU side, okay? Please keep in mind this, because it's important later. Now, another key point animation went all together, so it spoiled me the result. But okay, in any case, let's go ahead. The problem we have in the overall performance of a system is a concurrent factor of multiple stages. When we start the training, the GPU is idle while we prefetch the data and prepare the data. Then the train batch starts. Now, in an ideal case, we should take more training time than loading and pre-processing time. And this will be good, because this will, let's say, maximize the utilization of the computing portion, which is the GPUs, which is, by the way, the more expensive one, okay? In the real case, we can have some cases where per-processing time and data loading time is longer than the train batch itself. The gray lines below, I believe they are very little, is an epoch of ImageNet training. As you can see, the reading of the image folder is this slow, this very little bar. The full training is that black bar on top, and the reading and processes in this bar. So the limiting factor here is the pre-processing. But in any case, the efficiency of the system is not only due to the GPUs, but to the process itself. So we need a storage fast enough to provide the data, a CPU or pre-processing system fast enough to pre-process the data, and the GPU fast enough to complete training. Okay, so if we focus only on the GPUs, if we purchase only GPUs and everything else, this is going to be a problem because we are probably neglecting other important steps. Again, when do GPUs start during checkpoint? When I do the checkpoint, I just basically take a snapshot of the system. So I take the data in the CPU, copy the data in the system memory, and then flush the data on the disk. Now, there are several optimizations you can see over there to speed up the process. But in any case, for the in-memory to memory copy, the GPU stops, and this reduces the efficiency of the whole system. Okay? Again, we have a time component related to the memory and the time component related to how fast is the disk. Now, if we look from the perspective of the disk, we can say, okay, we just need a disk that is fast enough in reading, more or less sequentially, and fast enough in writing, more or less sequentially. Things are a little bit more complicated because, okay, in a sample, each sample is read sequentially. So, okay, we need the sequential read on write fast enough. But during the training, the system shuffles the read of the database, because this improves the ability of learning of the system. The learning ability. Just if I am a teacher and I explain you the book always in the same order, so the stuff following the same order is different than if I one time explain the book in sequential order, then we come back to an argument, then we go forth on another argument, and so on. This reinforces the training. And this creates a lot of reads and writes, which are basically sequential, pointedly, but in random order. So let's return to the storage perspective, okay? What storage we need to do this? We need the storage fast enough in read and write, because we have an incredible amount of data and an incredible amount of computing power. So standard parallel file system architecture with the separated metadata and data with the front ends and a bunch of disk on the back, and it won't work anymore, because we need performance. And that's the reason why we see the emerging technologies of distributed storage system, parallel storage, even scale-out storage system, because we want to have the firepower on the storage system more or less matching the firepower of the computing system. So traditional architecture doesn't work anymore. And also, the idea is that if we read a lot of data randomly, we basically are challenging the metadata system. And that's the reason why the insulated metadata, as worked for the standard parallel file system in the HPC, don't work anymore. This is the reason for the emergence of scale-out architecture that anybody of us have at their portfolio, basically for the AI workloads. Last but not least, a lot of existing AI framework basically work on standard parallel file system. So we have block access or kind of file-based storage solution. But there is an emergency of object storage that is maybe not good for training, for hosting the working space, let's say what we call the scratch space in the HPC notation, but useful for hosting the ingested data, because they can support intelligent features that help us to prepare the tensorial batch to be processed in the system. So we need the fast storage with a lot of solid-state disk, with a lot of firepower on the nodes, and that can have some intelligence somewhere in order to speed up the preparation process. Now, how we at Dell see a design of a storage solution, basically organized in a couple of 2 rings or 2 tiers, whatever the name you want. So there's a first ring or first tier, which we call the data lake, where you can put your data and include, conserve long-term persistent data and do some pre-processing work to make the data ready for okay, time is finished, sorry, I have only one slide. The data to be analyzed later by the training system. And the tier 0, very fast storage, very all-flash, GPU connected to run the training itself. We don't believe that one box can fit everything. We believe that the best and most efficient solution is to divide and conquer both phases of a training, basically. Now, I don't want to talk about data lake. There have been a lot of announcements in the past. There will be other announcements at supercomputing. I invite you to come to our booth, where we will announce a lot about storage and about cooling this year in St. Louis. Just a few words on the famous tier 0. We are going to launch at supercomputing what we call Project Lightning. This will have another name, but you know, as a joke, we named the project with a certain name. Now, actually, it's a Project Lightning that is adding parallel file system functionality very fast. So what we call the tier 0 in the format diagram, on top of the solution that we propose for AI trainings, which is our power scale, which is our scale-out solution. So we have changed the kernel of the system. We are adding functionalities. We are adding very fast NVMe solid-state drives in order to get the extreme performance we need for training and workloads, together with the intelligence in a single logical system that we need for preparing the data itself. I believe I can stop there because I'm 2 minutes out from my time. I'm sorry to be done this in a rush. I'm ready to take questions if you want, or I can take later. Thank you.
Public, or even from me. So now, Phil Reisner, CEO of LINBIT, fondatore e amministratore delegato di LINBIT e autore di DRBD. LINBIT è cresciuta, è diventata un fornitore internazionale di assistenza per software open source e HA cluster.
Thank you for the introduction. I will speak in English. No chance to have me talk in Italian. I guess I'm also scaled down to 7 minutes, so let's jump into it. Next. So I'm coming from a little bit different background. What we do is we take physical servers with storage devices in them and add software to that to build highly available block storage for cloud needs. So this is where we're coming from. But it's also usable in the HPC world. So let me give you an overview how all this works, what we are doing. And it's so easy to forget because it's so natural for me. Everything we do is open source software. So everything I talk about today is open source. So I'm approaching the topic from the bottom to the top. At the top, for me, we have the workload orchestrators. So that's maybe a Kubernetes, maybe an OpenStack, but also a few more like Apache Cloud Stack and so on. You see the whole list, scaling all the way to Proxmox. And they orchestrate workload for us, virtual machines or containers. And when they need persistent volumes to store data that should be safe against one of our machines failing or one of the storage devices in our machines failing, then this is something for the software stack we are presenting here. So all these workload orchestrators, we have plugins there. They connect to our API. It's a REST API. The REST API is provided by the controller component. The controller component, that's the stateful center of our control plane. In a usual cluster, you have like 3 locations where it can run. The other component of the system is the node agent. It's called the LINBIT satellite, LINSTOR satellite. The satellite itself is stateless and configurationless. So you start the daemon, that's it. And that's the whole control plane of the solution. And now let's move on to an example. So I'm looking here at a cluster of 6 nodes. So could be Kubernetes nodes, could be OpenStack nodes, right? Each of those has enough CPU and memory to run the actual workload, virtual machines or containers. And we have built-in storage devices, let's say a bunch of NVMe drives. When we get the request from the orchestrator, here's a new virtual machine, I need a virtual disk for it. So what we do is we store the data replicated, so at least 2 times. You also can have 3. We will co-locate one of the replicas with the workload itself. So that means that for all the reads, we can fulfill them locally. We don't generate traffic on the network. Only for writes, we send something over the network. So here in this example, we have the optimal layout, right? Each VM is co-located with one of its replicas. It can read with the full speed of the NVMe drive, no network latency added. To the writes, yes. Now, what happens if we migrate one of the VMs? Well, then storage access happens over the network. We get this small latency impact of the network latency, but okay. It's bearable. Either by an explicit action or as a time-triggered action, the system can check if there is enough storage space available at the location where the VM is running now, and if yes, it migrates the storage to the hypervisor where it's currently used, all in the background, completely transparent to the workload itself. After copying over all the blocks is finished, the replica, the third replica will be released because the storage policy in this example requires 2 replicas, not 3. That was the example for the control plane so far. Let me move on to the data plane since I'm a little bit under time pressure. So the data plane is realized by a Linux kernel driver. It's called DRBD. It's in the upstream kernel, but the version I'm talking about here, that's an external module. So it presents a virtual block device on the Linux level, if you're familiar with that. And in the moment you open such a device file, its internal state promotes to primary, and that dictates the direction of replication. moving a workload from one machine to another is very easy. You need to close it first, then you can open it on the other node. And with that closing and opening, these roles demote to secondary or promote to primary on the other side. There's a little trick for doing live migration, but that would be too much details here. It can do consistency groups. So that's important if you run huge databases and you have one type of storage for the table spaces and one type of storage for the write-ahead logs. Then you need to replicate two of those very different physical storage devices in a consistent stream where no write can overtake another write. It can do up to 32 replicas, but nobody needs that. So for redundancy purposes, we need 2 replicas, maybe 3. If you span it over multiple data centers and include your DR, disaster recovery considerations, you might want more, but not 32, right? The software can do synchronous or asynchronous replication, so also far away data centers. That's the most useful configuration, so that you have 2 full replicas for redundancy purposes, plus a third node that enables us to do quorum. And it also allows you to access the data there. So this is a pattern we see very often in the field. You have storage servers and compute servers separated. Although you lose a few of those advantages when going hyper-converged. So this is how all that looks when I look at the kernel level, right? So here the orange box, that's the operating system, the Linux kernel. And here we have this I/O stack, file system, buffer cache, etc. And this is where it inserts itself into the I/O stack. It can do synchronous and async, but today we are a little bit short on time. Where's all that used? So currently we make our revenue in the area of users that use it for virtual machines, for containers, and the types of workloads they're running is most often some kind of database, either if it's called database or if it's called enterprise message queuing system. Most of the time I call it transactional databases. Some of our users also do this analytic databases like warehouse, etc. Very often I get the question, what makes a difference from Ceph? Because Ceph is also open source. Ceph also provides me software-defined storage. Well, the difference is we are specialized in doing block I/O, and we are really fast in that. For reasons why this is. So we published a few performance benchmarks. If you get the slides, there are links to the papers that describe in very detail what we were doing there and measuring. And in summary, what LINBIT is doing, we are active in 4 areas. One is protecting your data. The second is helping you to keep your services running that access this data. With Shape Your Destiny, I mean that this is an open source company. If you bet on LINBIT, you can be sure it's not going away like VMware did. And we deliver very good performance in our field. I would say we are the best in our field. So I managed to stay in the under 8 minutes. That's it.
Thank you. You can sit. Antonio Colavincenzo, Pre-Sale Europe DDN. Data Direct Networks, la più grande azienda privata al mondo nel settore dello storage.
Grazie tante. Oggi... questo. Meglio questo. La mia presentazione... Mi fanno dei gesti straordinari. Che premo? Help me out, please. Come? Io l'ho mandata alle 3 di notte ieri. Okay. So I leave the stage to the next presenter so they can load my presentation up front. Sorry for the inconvenience.
Okay, doesn't matter. It happens. So Brad Painter, VP Global Channel Sales VDURA, he is of course Vice President, è la guida la strategia mondiale dell'azienda in materia di canali, compresi il reclutamento dei partner, la riabilitazione e la crescita negli ecosistemi di distribuzione dei rivenditori a valore aggiunto.
Well, I have to give it a DDN. That was definitely under 7 minutes, so well played. First of all, I want to thank the E4 team. Really appreciate this great event that they put on, in addition to giving me the opportunity to speak to you all. Again, my name is Brad Painter. I run channels for the VDURA company. For those of you that don't recognize the name VDURA, you might recognize the name Panasys. That was the company that we were previously. We've been 25, almost 26 years now of building and developing parallel file systems. So this is one of the slides that I really love. It really points out that the only certainty in AI workflows is that there is nothing certain about AI workflows. As we scale, as we grow, these things are going to evolve, they're going to change, and they're going to continue to challenge all of us between the data and the compute side. Now, as VDURA, what we try to do and what we are doing is we're putting together a solution that, in my opinion, future-proofs our customers so that as AI workflows adapt and the storage required adapts, so does our solution. So what you'll find is that we really try to protect your storage investment over time so that you can scale and grow as things move forward and you can do it at the right price. So we really focus in on 3 different things. We focus in on the economics, the performance, and simplicity. From an economics perspective, we really look at this as a way that we can bring you the best-in-class overall TCO, and we can bring you a solution that's going to meet your budget requirements. From a performance perspective, because we are a true parallel architecture, and we can offer both all-flash and hybrid solutions, we can deliver a high level of performance for you so that you've got that aspect and you can scale it and grow that. And then from a simplicity perspective, we are an enterprise level software. It's not a lab experiment. So when you plug this in, it's half of a day to a day at max to actually get everything set up and running. Typically takes about a half a head to run it ongoing once it's installed. So it's enterprise class. It's something that you can put it in, you can set it, forget it. And so we really try to stay on those 3 principles. Now, because we are a parallel performance file system, at the end of the day, the bigger the system gets, the more users that are using our system, the more resilient that we get, the more performant that we get, and the more durable we get. So I'll talk about durability in a minute, but we have a flash optimized engine that's in our director node now, and it's something that we have just unlocked in our V11 software, which launched back in June. And so that is a very high performance metadata engine that is in our solution. I'll talk about kind of where that fits into our model here in a minute. I talked about the resiliency, right? Our erasure coding, our redundancy in the way we set our systems up, we do not lose data. And so I can tell you there are a lot of systems out there that can lose anywhere from 10 to 20% data per year. We don't lose data. And then flexibility I'll talk about here next since we're rushed. This is the typical configuration for us, and I'll say that in a couple of ways. One, everything starts with the director node. So the director node for us is an all-flash system that includes all of the handling of metadata, so it has the metadata engine, and that's also where all the data comes into our solution. So everything comes into our solution on flash. Beyond the data nodes, we do have all-flash nodes, and then we also have all-flash hard drive or JBODs with archive solution. And so we can combine, first of all, we can be all-flash. That's fine. If you want all-flash, we can deliver all-flash. We can also deliver a hybrid, and we can go from a 2% flash up to 100% flash. It really comes down to your workload, it comes down to your use case, and it comes down to your budget and requirements. But when we do this, everything's under one global namespace, right? So it's managed from a common control plane. You don't have to go to a third-party product. It's very easy to manage and scale and grow as you move forward. If you look at the typical, the initial implementation for our solution, we always go with the 3x3. So it's 3 director nodes, 3 storage nodes. And the purpose for that is that gives us not only the performance, but it gives us the durability that you need in this solution. And it also gives you the ability to scale in 2 different ways. We can always add more director nodes. So if you really want that high-level metadata performance, you've got a lot of users, you can scale out the director nodes, and you can scale out as far as you want, really. There's no limit at this stage. But then you can also scale down below. And again, like I mentioned before, you can scale with both archive as well as flash. So when you look at the bar on the top in the gold, you know, I told you we could range from about 5% flash up to 100% flash. Just to give you an idea of the difference in cost, if you went all flash array with 20 petabytes, average street price on that's going to be around $10 million. If you went in with a 50-50 mix, 50% flash, 50% archive, you're now talking about $6.5 million. So I've heard consistently throughout the day there's that challenge between storage and compute, So if we can deliver you a system that gives you the level of performance because everything is input into the flash layer, but how much of your data really sits or should be sitting on flash long term? It's expensive, right? It's really expensive. So if you can offload the data once it's in the system from flash to a less expensive, we're certified with all the Seagate HAMR drives now, right? So we've got the 30 terabyte drives. As they scale into the 40s and 60s and everything else, those will implement immediately into our solution. So it gives you a really inexpensive way to store the data that's not hot any longer. So you free up your flash for the stuff that is important. And so we can mix that, we can match it, you can save money. I will tell you that today, the actual power efficiency in the rack is better in a hybrid environment than it is with all flash. So if your customers are concerned about power consumption, it also saves money on power. And again, you know, we can scale those systems as needed for the customer. And I think I'm going to make the 7 minutes here. So this is the last slide. Just to cap it from a performance perspective, true parallel, extremely fast, extremely durable. We do exceed NVIDIA's read and write performance requirements for SuperPod. And then the flash-optimized metadata engine works extremely well. And so it's something that we've just launched in the last product that's launched back in June. From an economics perspective, we can save anywhere between 50 and 60% of the overall cost per systems based on being able to go in with a hybrid versus just going in with all flash. Now, by the way, as a customer, you could start with all flash, and then as you want, you could add disk to the system because it is one global namespace. It's not a third party. It's very easy to implement that way. So you can start hybrid. You could go hybrid later if that's what you want, but it gives you the option to pick and choose when you want to do it. And that's why I mentioned future-proofing. Let me drop, we do have a 10-year guarantee as well, so we will do 10-year contracts on the products, the drives, and the solution. And then the only other thing I want to bring out is, depending on how you want to build the system out and configure the system, we can go anywhere from 4 nines of availability upwards to 11 nines of availability. So when I say we are durable, I mean it. You know, we can certainly build this system out, and if your data is important, and if you can't lose that data, and you need redundancy around that data, and you need to have data accessible, we can make that happen. So I think I'll leave it there. I think we'll have questions later, right? Okay, I have 8 minutes. There we go. Thank you.
So the magic of editing. I'm Antonio Colavincenzo, Pre-Sales Europe for DDN. This is not a product presentation. We want to talk about the data intelligence platform. Is the approach of DDN to the AI and HPC storage symbiosis, as the panel title says. So what is DDN you already know. We started, as you can see here, as a data provider, and we moved today as a global provider across all the technological stack. So the point is, DDN now is not just, providing a fastest block storage or a fast file system, a very capable infrastructure, but it's rather a partner, let's say a partner in crime for your AI technical outcomes. This is not a business presentation for me. So how we want to do this? What's the story so far, the challenges? So we started as providing a parallel file system, meaning remove all the bottlenecks between the storage and the compute. So a full RDMA paradigm, it's on the left-hand side, and when GPU emerged, with GPU direct storage, we bring these truly parallel down to the GPU file system capabilities at the compute level, where the computation is. And then the first stage is remove the bottleneck. The second stage to, complement the solution so far is enrich it with new features such as, standard protocol capabilities to, as I said here, open the HPC vault. So expose the data, not only the storage, but the data outside of the typical HPC pillar into the bigger organization. And we did this with, data-centric access, so seamless multi-protocol access for the parallel file system, rendering it accessible as, NFS, SMB, or S3 storage, as well as facilitating, containerized workload with this very, very important read-write-many feature, meaning RDMA down to the container. So this means your containers can really leverage the parallel file system. But there is more, right? So the point is not, just make the car go faster, make the car go further with novel capabilities, but today's challenges are at the very core of the data fabric. So we, DDN, are the file system experts, and we do challenge file system structure itself. As you can see here, typical file system is not optimal, is not an optimal data storage for the present day workloads, because data structure in files and directory is meant to be human readable and human organized. The metadata that we have today, like file name, file size, owners, and Unix permissions, are not enough to describe all the data capabilities. And also, directory structure can be confusing, and a flat layout of a humongous amount of data it means rendering any file system on the brink of uselessness. So we do believe that, the cyclic or acyclic tree, which is a file system, cyclic if you include symbolic link, but should be acyclic graph, is not sufficient anymore for the present tense. So we have to challenge to tackle the novel challenges with a different approach. So Exascaler It's all about removing bottlenecks and delivering line performance. And to do this, we excel at this with maximum bandwidth, and of course, rooted in HPC, spun off to the AI, is still the best solution for GPU training, like any other parallel file system from any vendor. This is not, a product presentation. But Infinia, the other thing we are developing, is more around consistent low latency and this new metric, time to first byte, to facilitate and be the best for GPU inference. So, okay, so I have a problem with the slides, as you can see, but the point is, the Infinia data plane is a scale-out key-value store, so it's not a file system, it's not a block device. This means that it renders data and metadata seamlessly. For us are the same. We only data sizes matter. Protocols like S3, file, SQL, or CSI are just, data views and they will blur into a Infinia API SDK, making the data plane itself accessible for your application. So today we have, Spark Accelerator for S3 or HDFS. We have Trino Accelerator for S3. We do very well with Rapids, with GPU direct support, as you know. But if you if you really have your own PyTorch code and you wanna write into the data platform, you can do that programmatically with API. This is what I told you. The key thing here is Infinia is all built in microservice architecture, so you can really blur the line between compute and storage, deploying the microservice anywhere in the technological stack. So for instance, in this scenario, this is a traditional environment where you have an S3 server in our platform, and you just talk S3. But if you move the S3 server into the client, you talk S3 with localhost, and enable RDMA for an S3 workload, which is not a thing today, and leverage, the parallel rights of many Infinia servers. And this allows you to also include, new technologies in the mix, because this player here, either on client side or server side, is just another compute element in the software stack. I'm sorry if the slides are not, readable, very well readable, but you see the point. You can offload features to Bluefield and or to any software stack, rendering Infinia a global data platform. Thank you.
Thank you. So the last one for this panel is Daniele Piccarozzi, Senior Market Development Manager, AMD. AMD is Advanced Micro Device, è un'azienda globale produttrice di semiconduttori fondata nel 1969.
Grazie. Ok, salve a tutti, grazie per la partecipazione. Allora, credo che abbiamo poco tempo, quindi andrò veramente al cuore di queste poche chart che avevo preparato per condividere un pochino con voi qual è la strategia di AMD nel mondo dell'AI e dell'HPC. Allora, AMD probabilmente, credo sia abbastanza conosciuta, sono più di 50 anni che produciamo processori, GPU, qualunque tipo di microarchitettura, e AMD al momento... Oh, sorry very much, I'm realizing now that I'm talking in Italian. Sorry for that. So, especially for our English-speaking friends on the bottom. So sorry for that. So, okay, let's quickly start again. AMD leading in the semiconductor industry, more than 50 years, producing all the sort of devices, and currently powering the most powerful supercomputer on the planet. You probably know number one in top 500, El Capitan is based on AMD technology, providing more than 2 exaflop. You probably know the most powerful supercomputer in Europe is based on AMD technology and installed at ENI, close by here in Milan. And as well, the most powerful supercomputer in the commercial HPC space. The most powerful supercomputer in the European research ecosystem installed at Lumi in Finland is based on AMD. So as you can see, we are very, very strong in the HPC space, very used by all the leading community and research institutes. What I would like to share today very quickly, and let me jump some chart as we just have 5 minutes, is the core of AMD's strategy when it comes to AI and HPC. So I would say our pillar for our products. The first pillar is our leadership in compute engines. So our CPU, our GPU are the most powerful you can find on the market in terms of spec, in terms of flops that we can provide. And one thing that I would like to underline is that it's not just about CPU or GPU, but we have a very broad portfolio of devices that span from the CPU to the FPGA to the embedded device. CPU, of course, is particularly important. Our EPIC product line, we had a huge market gain in the past 10 years. Now we are 40% of the market, and we power all the largest cloud and enterprises. And the GPU offering, our AMD Instinct one, we are now releasing one iteration of this product every year. The 300A is what you see there, powering the El Capitan, so the 2 exaflop system. And since then, we've been releasing one iteration every year, and next year we are going to announce our next generation of MI400. One thing I would like to underline about our offering here is that we keep serving both the HPC and AI space. So we see in the AI space a strong focus on low precision math. That's very good for AI, but it's not very good for all the kind of HPC application that the HPC space community is used to run. So across all our product line, we still support FP64. We still plan to support FP64 in the future. We still plan to serve both the HPC and the AI space. On top of the most powerful hardware that you can buy on the market, we strongly believe in open ecosystem. So that's why our software philosophy is based on open source and open innovation. We comply with the standard of Ultra Ethernet and Ultra Accelerated Link for the hardware side. We provide all our software, infrastructural software, free of charge and open source, so that can be fully controlled by our customer, and you have full control of your environment. This is something that's particularly interesting here in Europe, where there is a lot of effort across different nations to take control over technology, to build over sovereign technology. And I mean, we think that providing our platform in an open source fashion is the best way to enable these sort of initiatives. We are collaborating with a broad number of European entities. I mentioned a few of them before, and here you have a broader spectrum, but we are very open to collaborate, to have joint center of excellence, to have joint research activities with our customers and with the European community in general. And one particular note is on Salo AI, which is a European company based in Finland that have been acquired by AMD a couple of years ago. Silo is probably the largest AI community based in Europe. We have now them full part of our team, and we are collaborating with Silo of a number of European initiatives that you can read here. And they've been working a lot on the Lumi system in Finland, helping the development of very large language model based on European technology. One last mention, I show very briefly the three pillars, so the high performant hardware, the open software, and now the integration. So we've been announcing recently our coming integrated solution that will be announced in 2026, and we will start integrating all our compute capabilities and networking within reference design that will speed up our OEM capability to implement our solution on the market. Final chart to close, that we are deeply engaged with the developer community, as I said before, with a number of European institutions, but we are also running hackathons. So if you are interested in AMD, in knowing more our technology, please reach out to me. I'm here at the event for the rest of the day. You can reach me via email, or you can just go to our website and learn more about our activities. Thank you.
Keep it. No, keep the microphone so you can answer to the question. Are there questions from the public? Oh, today everybody's shy. Then don't do like before, at the last moment, they raise hand when the time was out. Nobody? Okay, that's one question. Is there a mic? Okay, it's arriving.
So, as AI training scales, and to thousands of GPUs, and there we have different components. We have talked about metadata, ops. We have talked about small files. We're talking checkpoints, bursts. We're talking about different factors, which are like critical, not only as raw throughput. So all of this together. So how does your architect handle these non-sequential workloads without stalling accelerators?
For who?
Well, I think all of them, they are storage experts. So
okay, you can choose. You are rich. You can choose
I will start with the biggest actually site in the storage. I believe DDN will be just a good candidate to answer.
Okay.
So yeah, of course, thanks for the question, Hussein. The key thing is I want to add another element. So today we see the introduction of asynchronous checkpointing. As Paolo mentioned in his presentation, and this is the warhorse of DDN to have, let's say, a very strong file system capable of minimizing checkpointing, model load, and data load time to give you more bang for your bucks in terms of GPU time in return. Our CEO today said DDN is for free because in a year you repay your storage in terms of GPU time. Yeah, but how? This is your question. So on the very technical standpoint, the all the parallel file system with their own, with each and every one's secret sauce, they manage to somehow alleviate the randomness of the random I/O, and to withstand with various technologies the randomness of writes, which is the most significant one, and this is the one when we have the more and more engineering focus on the software standpoint. For random reads, for model load and data load, we as DDN are pretty comfortable because we don't see that as a bottleneck so far, but we are introducing GPUs in the hundreds and hundreds of thousands. So even asynchronous checkpointing, that means linearizing, let me say, the checkpointing I/O, and giving you more time between the epochs to to actually perform the checkpoint, will not be a break for us, but will introduce more challenges for the storage, because we see an increasing checkpoint cadence, so forth. So the technological standpoint advanced. There is no break for us. We still are very, very strong on the edge of true performance.
Thank you. Paolo Bianco. Can you tell us something more about the project Lightning, how the data lake relates to the data lakehouse paradigm? It's not my question, so I'm just reading. Like before with Professor Floridi, is someone from the public.
We will have some announcement at supercomputing, so I can say something but not everything, or I will be fired immediately after 5 minutes, because I'm spoiling. It's my boss here, so we're ready. Yeah. So basically what we are doing is creating a single logical entity where we handle differently the data depending from the needings. Okay. So as we all of us have talked, there is a need for performance, outstanding performance, because we have an incredible amount of data and an incredible amount of computing power or GPUs somewhere, and we are going to handle this with the new Lightning parallel file system functionalities. I believe it's not a secret that the power scale itself is running on a parallel file system. It's not a secret if you buy any, computing book, university book, the file system, underlying file system is considered a parallel file system. We are integrating our, parallel functionality, new parallel functionalities with existing object storage functionalities under the single hat, so that we have a consistent view from a host perspective, but we handle the data differently if we have to prepare the data or we have to read the data. That's basically, as I shown, we have two separate stages where we need and prepare the data. We need a certain kind of computing power and certain kind of I/O that is already existing in our data lake, and we need an outstanding I/O power for the training. So that's Lightning is basically adds these functionalities and put hand and head on top on, let's say, creating a different hardware solution under a single logical head. This is all I can say right now, sorry.
Okay.
But I encourage you to come to our booth at Supercomputing, where we have a lot of announcements. Please.
They said that we are late, so there are no more questions. I'm sorry. Okay, thank you. You can come back, and we pass to the next round table. Grazie.